All right, so let's do this. So, as talked about last week, the second half of this chapter is going to be dedicated to acid-base reactions, something that you talked a little bit about in Chem 1A, did a little bit more in Chem 1B, and now we're just going to expand upon that in organic chemistry. Of course, focused on structures a lot in this course. Okay. So first of all, just kind of a reminder. Let's get down an acid-base reaction. HCl plus hydroxide gives us water and that chloride ion. All right, we got some terminology. First of all, HCl is our acid and hydroxide is our base. All right, we have these definitions for acids and bases. An acid is defined as a proton donor, right? Remember those hydrogen ions we just simply call protons because when you make a hydrogen ion, you take the one electron away from hydrogen, leaving just the proton behind. And a base is then the opposite. It's the thing that's accepting that proton. So a proton acceptor is a base. Okay. So in our above example reaction here, you can convince yourself that HCl gets rid of this proton. It donates it to the base. All right. We also had some fancy terminology for our products here as well. Our acid, once it donates that proton and becomes the chloride ion, we call that chloride ion its conjugate base. Okay, so an acid is paired with its conjugate base. And likewise, our base, once it does its job and accepts that proton, it becomes the conjugate acid. All right, so important definitions. Our acid is a proton donor. Our base is a proton acceptor. But also on our product side here, we have these terms. Our acid becomes the conjugate base, and our base becomes the conjugate acid. All right. And again, just review from last semester here. One of the first things we need to be able to do with these acid-base reactions is predict our products. We called these our conjugate pairs. All right, so for an acid, we want to be able to give the formula for its conjugate base. All right, so our one that we started out with, HCl, we said that becomes the chloride ion. And we can kind of use this as an example to figure out how we go from acid to conjugate base here. What did we do to this chemical formula? Well, again, the acid has to get rid of that proton, that hydrogen. So we decrease the number of hydrogens by 1. But importantly, that hydrogen that it gave away had that positive charge. So we also have to decrease our charge by 1. All right, so then using this logic, everybody's going to take a second and give me the conjugate base of these following acids. water is going to lose that hydrogen, lose one hydrogen. So now we're just down to one H and our oxygen. And then we take our charge down as well. And we have a special name for this guy. He appears a lot in acid-base chemistry. What do we call that one? Hydroxide. All right, same thing here. This hydrogen sulfate here, if it donates that hydrogen, we're just at SO4. But again, we got to take down that charge. So if we had a charge of -1, now we're going to have a charge of -2. All right, so just being able to predict our products here. So now what if we start out with a bunch of bases and we need their conjugate acids? All right, again, from our example at the beginning of class, we had hydroxide. Let me write this a little bit differently. And that got converted into its conjugate acid, water. All right, so what did we do to our formula here? The base accepts that proton, so we're going to increase our number of hydrogens by 1. And it didn't just accept a neutral hydrogen atom, but rather that positively charged hydrogen ion, so we're also going to increase our charge by 1. All right. Common organic bases contain nitrogen, so let's do that example, as well as we'll put water down as well. All right, so you're going to take a second, give me the conjugate acid for these following bases. All right, so NH3 becomes NH4, and we're going to increase that charge. So it's going to have that positive charge. If water's a base, again, we're going to increase the number of hydrogens. So now I'm H3O and increase our charge. We see this also a lot in acid-base chemistry. It also has a fancy name. What is that? Hydronium. Okay, and we see water as, in both our acid and our base table, and this was an important sort of update from the way that you had first learned about acids and bases. When you first learned about acids and bases, they were like a class of a chemical. So an HCl was this acid, and hydroxide was this base. But really we need to update our way of thinking about acids and bases because there are a lot of molecules that can play the role of both. Water is a great example. Sometimes water is acting as an acid and donating a proton. Other times water is acting as a base and accepting a proton. An acid is anything that is playing the role in the reaction of a proton donor, and a base is anything playing the role of the proton acceptor, right? So these are really roles that these molecules are playing in a chemical reaction, not like a class of chemicals. All right? All right, we're going to spend a lot of time, actually probably the whole rest of the day here, talking about the strength of acids. Okay, and a big update from what you had learned previously when we were talking about acid strengths. Previously, we divided the world up into strong acids and weak acids. Okay, now we're going to compare acids on like more of a sliding scale. All right, so first of all, what do we mean by a strong acid? This is something that donates that H plus very easily. In fact, donate is probably a little bit too nice of a word because it sounds like it's this, oh, here you go, have my proton kind of thing. A really strong acid is forcing that proton on anything around it, right? So HCl, for example, why it's so dangerous is because that hydrochloric acid is going to put that proton anywhere it can find a place for it. It's going to force it upon something else, right? A weaker acid, let's say stronger acid and weaker acid. This means that that proton is harder to remove. All right, so this is what we need to keep in mind when we're talking about acid strength. We're talking about how easily that proton gets donated. Okay, we're going to do two examples down here looking at organic acids and bases. And we're going to look at what we called last semester our acid dissociation reactions. All right, so our two organic acids that we're going to look at are acetic acid, and you don't have to know the names of these yet. There will be a point in the course where you do, but we'll cross that bridge when we come to it. Nonetheless, I'm going to throw them around here. This one's acetic acid, the active ingredient in vinegar. And the other one is ethanol. All right. Like I said, these are going to be our acids in these chemical equations we're going to write here. And in our acid dissociation reaction, we always had the same thing playing the role of the base, and that was water. All right, so given what we discussed about predicting our products for these reactions, I want everybody to take a second and see if you can't give me the products of these acid-base reactions. Again, our organic molecules playing the role of the acid, and water here is playing the role of the base. Bless you. All right, so first of all, they both have the same conjugate acid, which is what? Hydronium, right? My base, my water, is going to accept a proton. I'm going to draw this in a little bit of a weird way here just to make a point. I'm going to show that new bond explicitly here. Give that a plus charge on that oxygen. All right. And then my conjugate base here, I need to take my acid and I need to donate that proton, right? So this is the proton that I lost to the base. All right, but as we discussed before, we also need to take that charge down as well. So that oxygen, it loses that proton, and now it has a formal charge of -1. Okay? Now, importantly, and we'll talk about mechanisms next class period, we'll show this a little bit more explicitly using our electron pushing arrows, but just to note here, this bonding pair of electrons in my acid, between that acid and that donatable hydrogen, that's that lone pair. That's that same pair of electrons that becomes my lone pair in my conjugate base. Likewise, in my base, you'll see that your bases always have a lone pair on them, and that's because it's that lone pair that's forming that new base hydrogen bond there. All right, so those pairs of electrons that are colored orange on the left is the same as the lone pair colored orange on the right. Likewise, the lone pair on the left becomes my bonding pair when that new bond forms. All right, so given that, everybody take a second and give me my formula for my conjugate base over here based on what we just discussed. Not my formula, sorry, my structure. We need to get rid of that hydrogen on that oxygen and give it that -1 formal charge. So according to our bonding patterns, that means it should have 1 bond and 3 lone pairs. Okay, I guess just to finish this off, this was our conjugate acid and our conjugate base for each of these reactions. Okay, all right, so now our discussion was all about the strength of these acids. So we need to be able to look and figure out which one of these two acids is stronger, my acetic acid up top or my ethanol down below. Okay, we're gonna have 2 different ways of doing this, 2 different approaches here. So one, we can quantitatively compare acid strength. All right. These acid dissociation reactions, if you remember, you did a lot of math with these last semester in Chem 1B. You could actually predict what the pH change was going to be and all that jazz. And that's because for these acid dissociation reactions, we can look up their equilibrium constants, what we called their Kas. And that would tell you how favorable this reaction is, how much it favors going in that forward direction, where your acid donates that proton. All right, so we can use those same equilibrium constant values to compare acids, how favorable it's going to be for that acid to lose its proton. All right, we actually prefer to use, instead of Ka values, what are called pKa values. So we're going to use the pKa values for each acid. Okay, the stronger the acid, the smaller the pKa value. pKa's were the negative log of those Kas. So if you take the negative log of a big number, you get a little number. All right, so the stronger the acid, the smaller the pKa value. And just like before, we had this big old table where we were looking up these equilibrium constants. We will have this constants page for this chapter as well, which is a list of a bunch of organic compounds and the pKa values for those organic compounds. All right, you can see that they're listed in these kind of condensed structural type formulas, really just to save some space. All right, so I'm going to give you a hint. You're going to be looking somewhere over here, and you're going to try to find the pKa value of our acetic acid, right? So reading this table here, remember we talked about reading these condensed structures. So we drew out our bond line structure here. We need to be able to find the condensed structure on this table. All right. And again, for the sake of time, I'm going to tell you, you're going to look over here somewhere, but everybody take a second and find what the pKa for our acetic acid is. Anybody got it? Now the 4.8, right? So this right here, CH3, that's right there. C, we got our double bonded O and our OH, right? So acetic acid here has the pKa of 4.8. Okay, our other one is down here at this portion of the table. I've of course used this table a ton, so I kind of have an idea of where everything is. All right, but now you're going to find ethanol. All right, again, I'm going to tell you, you're going to look somewhere in here. All right, so here's a CH3, here's a CH2, and then our OH. So I'd be looking right here for ethanol. Okay, so going back here, just to update, we said our pKa of our acetic acid was 4.8. Our pKa of ethanol was 16.0. And so that means that which one of these is the stronger acid? The one on top with the lower pKa value. Okay, just to go back to our chart, you can kind of convince yourselves by looking at these as well. The things that we think of are as very strong acids, hydrochloric acid, for example, has this very, very small pKa value. All right, so yes, smaller the pKa value, the stronger the acid. Okay, so when we're quantitatively comparing acid strength here, we're looking at our pKa values. Okay, so really what we're sort of thinking about is our stronger acid. This means that that acid dissociation reaction is more favorable. All right. These acid dissociation reactions where your acid donates that proton, if this reaction really strongly favors this forward direction here, that's a strong acid. If it doesn't strongly favor that forward direction, it's a weaker acid. Okay? And again, we like these Ka values because they're tabulated, so we can go to our little constants page and look up the value for our acids. Okay? One thing I will note is that obviously, not all acids in the world are listed on this chart. So sometimes you can just want to try to find the molecule that most closely resembles your molecule. So for example, note that our alcohols, as well as water, those OHs, they all sit about in the same place on our table here. So if I had, let's say, instead of ethanol, I had butanol, something with 4 carbons. Well, I can approximate its pKa using that of ethanol. It's going to be around that 15 to 16 mark, right? So you can get an idea just based on a similar molecule if you can't find an exact match on the table. Cool. All right, so that's how we can quantitatively compare acid strength. That's kind of the easy way, right? If we can find it on that table, great. We can actually put a number to it. Okay, but how do we qualitatively compare acid strength? All right, so first of all, what we need to keep in mind when we're going to be, so I guess right now, by qualitatively compare acid strength, I mean looking only at our structure. So we want to be able to look at the structure of a molecule and be like, yeah, I know that's a good acid compared to this one. Okay? And there's going to be a really important principle to keep in mind here as we're going, is that a stronger acid has a more stable conjugate base. So we're going to be looking at structural features here. But really, we're not so much concerned about the acid. We're going to really be looking at the structural features of its conjugate base, because that's the key to how strong that acid is. All right? Going back up here, just to kind of make a point, we said that acetic acid was a stronger acid than ethanol. But the way that I can tell that just by looking at the structure is by comparing the conjugate base of acetic acid to the conjugate base of ethanol. The fact that this molecule is so much more stable with that negative charge than this molecule is how I know that acetic acid is a stronger acid, right? So an acid is going to be very willing to give up its proton if it's nice and stable without it, right? So that's what we're looking at, is our structural features of these conjugate bases to figure out how strong our acid is. Okay, so again, this is just super important to keep in mind. Our stronger acid means we have that more stable conjugate base. That's the key to life here. Okay, so there's going to be 5 things that we're going to be looking for in our conjugate bases to figure out how stable or unstable they are. All right, and we're going to rank these from the most important to the least important. And we're going to use this acronym FARIO to help us out. Okay, so our most important feature here, the F, stands for formal charge. We've already talked about a good bit about how formal charge corresponds to the stability of a molecule, so that's kind of the first thing that we're going to be looking at. All right, if that's a tie, we're comparing 2 acids and they both have the same formal charge. All right, then we're going to go down the line here. The next thing, the A, stands for which atom is donating that hydrogen. So it turns out that certain elements like chlorine are better at donating hydrogens than, say, oxygen, right? So the atom that's donating that hydrogen is important. The R, we're going to look for any resonance stabilization in our conjugate base. Right? Resonance, anytime you can draw multiple resonance structures, that means that you're looking at a more stable molecule. The I, this is going to be a brand new concept that we're going to have to throw at y'all today. What's called induction. All right, and then lastly, the O stands for the orbital, or more particularly the hybridization of the orbital that's donating the hydrogen. Okay, so these are, again, like a ranked list of what's the most important, the formal charge, then the atom, then if there's any resonance, then induction, then the orbital. The orbital is actually the least important here. All right, but let's go one by one through these and kind of compare each one here. All right, so first of all, the F, our formal charge. Okay. I'm going to put down 3 acids, and we're going to compare them to figure out which is the strongest and which is the weakest. All right. Okay, cool. So we're going to compare these 3 acids to figure out which one's going to be the best at donating that hydrogen, right? They all got a hydrogen that they can donate here. Which one's the best at doing it? Again, before we can figure it out, what we really want to look at is the conjugate base of each of these here, right? Because again, the one that's the strongest is the one that's going to have the most stable conjugate base. So everybody's going to take a second and give me the formula for the conjugate bases of these molecules. Okay, so I'm going to get rid of one of those hydrogens and take down my charge. I'll replace it with a lone pair. Same thing over here. All right, so let's take a poll here. We're going to call this acid A, B, and C. Looking at those conjugate bases and thinking about what's the most stable. What do we think is the strongest acid? A, because its conjugate base is this neutral molecule here, right? So since this, is the most stable. And we didn't even talk about bonding patterns with a -2 formal charge, because you're just never going to see it ever. This guy over here is very unstable. That's what makes this our stronger acid, and this one over here our weaker acid. All right, and so we can just note here our acids with positive formal charges will produce neutral conjugate bases. Which are nice and stable. All right, if we go to our pKa chart, indeed, if you look at that list of the strongest acids, you will see a lot of them have these positive charges, right? Again, because that means that their conjugate bases will be neutral. Okay, so formal charge, super important. The next thing, the A is for atom. Okay, and specifically we're talking about looking carefully at the atom that's donating that H plus. Okay, so going back to our previous example that we just did, we would be talking about our nitrogen here. That's the one that's losing that proton in this reaction. And the ones that we did the whole chemical equations for, we were looking at oxygens. These were our atom that was donating our protons here. So it turns out that certain atoms are better at donating protons than others. All right. If we're going to compare, there's actually two things that we're going to be looking for, depending on whether we're talking about atoms that are in the same family, in the same row on the periodic table, versus atoms that are in the same column. All right, so across our periodic table, all right, so again, let's look at some acids. And I'm going to go to our periodic table here, and I'm going to pick one of these rows. Let's take a look at these elements that we see over and again in organic chemistry and compare how well they would donate protons. All right, so I want carbon, nitrogen, oxygen, and fluorine. All right, we got to have the smallest possible carbon that we could have would be CH4. Nitrogen would be NH3. Oxygen would be our water, H2O. And then fluorine would be HF. All right, and again, in order to compare how strong these acids are, I don't really look at the acid, I look at its conjugate base. All right, so now we're going to take a second. We played this game over and over again. This is going to be an important part of this particular chapter here. Let's get the conjugate base formulas for these four acids. All right, so what do we think? Let's go again. A, B, C, D. What do we think the strongest acid up here would be? Why D? Cool, so this one right here is indeed the most stable of our conjugate bases. Notice that they're all tied at the F, right? They all have the same formal charge, okay? So the question is, which atom is the most happy to have that formal charge, right? If it has to have a negative charge, who's going to be the one that can bear having it? And yes, it's going to be our fluoride here because fluorine's the most electronegative element, right? Most electronegative element is the one that's happiest to have that negative charge. So this one's our most stable, meaning that that HF is our strongest acid. As your electronegativity decreases, they get madder and madder to have that negative charge. Hydroxide, have we seen this in the wild before? Yeah, so it exists, but it's not terribly happy, right? It's a pretty reactive molecule. We're pretty worried about getting it on our skin. You've never seen this guy out in the wild before. It is used in some industrial settings, but is super dangerous to use. And then you will just absolutely never see this guy out in the wild, right? Like this is just about the strongest base that you could ever possibly dream of. So yes, carbon not being electronegative enough, super pissed off to have that negative charge. This is our least stable, which means that those hydrocarbon compounds are terrible bases. I'm sorry, terrible acids. Holy cow. You're going to have a hell of a time getting that hydrogen from that carbon. Okay? So across the period, what we're looking for is electronegativity. All right, if we go down the periodic table, what we call a family of elements. There's actually a factor that's even more important than electronegativity that kind of dominates that behavior. All right, so let's pick a family on our periodic table here. We're going to go with our halogens. Okay, and again, we're going to look at a bunch of acids. So hydrofluoric, hydrochloric, hydrobromic, and hydroiodic. And if we compare the stability of their conjugate bases, we'd be comparing the fluoride ion, the chloride ion, the bromide ion, and the iodide ion. All right, and for this one, we're going to cheat. We're going to go to our quantitative cheat sheet here, and we're going to see if we can't find the trend of what our strongest versus weakest is. What do we got? Which one's our strongest one up here? Just about the strongest possible acid that you can have with a pKa of -10 is hydroiodic acid. Pretty close behind at -9 is hydrobromic acid. HCl's down here at -7. And HF we're going to have to hunt for on this chart a little bit. Oh, there it is. At 3.2. All right, so then which one's the strongest? I guess I kind of said it already. Anyways, the ones with a lower pKa, this is the strongest, and this is the weakest. All right, so then that means that the iodide ion is the most stable, and the fluoride ion in comparison up here is the least stable. And why might that be? The size. All right, so when we're going down the period, there's something that's even more important than electronegativity: atomic radius. All right, well, so why would that be? Okay, why is this bigger ion more stable than a smaller ion? Okay, so that bigger ion, all of these ions has to have that extra electron that gives it that net negative charge, right? And again, things don't like to have that net charge. But what's going to make it a little bit more okay is if you're something big and gigantic, your extra electron is going to be added to a very large orbital where they're all nice and spread out. Whereas if you're really teeny tiny like fluoride, that extra electron is going to be packed in close to a bunch of other electrons, right? So how much these electrons are able to spread out is what's influencing their stability. Large ions can spread those electrons out over a much larger area than smaller ions. We just reset the alarm up top. It doesn't like that water bath in there. All right, so this one's the most stable because our larger ion can spread that negative charge over a larger area. The electrons in the iodide ion are much more spaced out than the electrons in the fluoride ion. Okay, so if we're going across the period, it depends on the electronegativity. We're going down the period, it's the size. Cool. All right. The next one, the R, is resonance. Okay, remember, as we discussed last week, resonance can stabilize charge on a molecule. So again, atoms don't like to have formal charge. One of the things that makes it more palatable is if it can spread that charge out across multiple resonance structures. All right, so this is the qualitative feature that's going to allow us to compare those two acids that we discussed at the beginning of class, where we cheated and looked up their pKa values to compare them. All right, so we already cheated. We know that this one's the stronger acid, and that ethanol here is the weaker acid. All right, but again, what we should be doing is looking at their conjugate bases and comparing the stability of those conjugate bases. All right, so which one of these two, the one on the left or the one on the right, has other resonance contributors that we can draw here? The one on the left, this would be our allylic lone pair pattern. So if we're being good and we're representing the true structure of this molecule, we can't just draw our one resonance contributor, we should draw them both, where we show that pair of electrons and really that formal charge bouncing between those two atoms. All right, and the fact that I can draw these multiple resonance contributors means that we have a resonance stabilized molecule here. Again, that negative charge isn't just isolated to one of those oxygens, it's bouncing back and forth between the two of them. Really not bouncing, that's the opposite of what I told you to think about. It's simultaneously spread out between the two of them, which is stabilizing that negative charge, right? So this one over here is more stable because that negative charge is stabilized across multiple resonance structures. This one's least stable. Right? Remember, we had that term delocalized. This negative charge is delocalized across these two oxygens here. All right, so now we get down to the I here in our FARIO acronym. And the I stands for induction. Okay. Let me show you some acids that we can compare using induction here, and then we'll sort of talk about the difference. All right, we're going to take acetic acid, but then we're going to start decorating this last carbon over here with a bunch of halogens. All right. We're going to do the same thing, but only put one of them on there. And we'll compare this to just normal old acetic acid. Okay. Cool. And again, when I'm talking about comparing acid strength here, am I looking at the acid? No, we're looking at its conjugate base. So for the sake of being lazy, you can just erase that hydrogen and replace it with a lone pair and a negative charge. I got an iPad, so I can just do the copy paste and save myself some time. All right, but I'm just going to erase that hydrogen, replace it with a lone pair and a negative charge. Okay, so if I look carefully at my conjugate bases, we can just convince ourselves that we're tied for all the other parts of our FARIO acronym, right? They all got the same formal charge. They're all on the same atom. They actually also all have resonance. I can draw 2 resonance contributors for each of these here. So the only difference is the presence of those chlorines, but they're located kind of far away from that negative charge. Right? And that's exactly what induction is it's these electronegative atoms' ability to stabilize negative formal charge through neighboring atoms, right? So we know that those halogens are very electronegative. They pull electron density through their single bonds. They're able to pull some of that electron density away, even from all the way over there, all right? So induction This is an electronegative atom's ability to stabilize negative formal charge through bonds with neighboring atoms. All right, and somebody sort of pointed out last class that that kind of sounds a lot like resonance. And it is pretty similar, but way weaker than resonance, right? Resonance was even higher on our list. Remember, resonance always occurs through like pi bonds and lone pairs. These are through single bonds here, and it's way, way weaker of a stabilization effect, but nonetheless still has an impact, all right? So in this case here, the one with the most halogens has the most inductive stabilization. So this trichloroacetic acid is the strongest. And regular acetic acid without any sort of stabilization through induction is the weakest. Okay. All right, we're going to do one more induction comparison here. Let's take our ethanol. But one, we're going to put a halogen on carbon 1. Whoops. And in the other, we're going to move that halogen over to carbon 2. All right, I want you to take a second and think about it and tell me which one of these is stronger and which one of these is weaker out of the two. All right, and remember, really what I want to do is not look at the acid, but look at its conjugate base. All right, so let's take a poll here. A or B, which one do we think is more stable? Who thinks A is the more stable one? And who thinks B is the more stable one? So why A? Because it's closer to that negative charge, right? So its ability to stabilize the negative charge is that much better if it's closer to it. So again, this electronegative halogen is going to pull electron density. Well, it can stabilize it much more effectively if it's right next door than if it's 2 carbons removed. All right? So yes, this one over here is more stable, meaning that was my stronger acid. This one's less stable, meaning that one's my weaker acid. All right, so in addition to how many halogens, the proximity of those halogens also matters when we're talking about these inductive effects. All right, and then the last one on our list here was orbital. Specifically, we're talking about the hybridization of the orbital that's donating that hydrogen, that proton. All right, so looking at our three different hybridizations, we could be sp3 hybridized, sp2 hybridized, or sp hybridized. All right, let's just get a simple example of three hydrocarbons that have these different hybridizations here. So we're going to look at ethane, ethene, and ethine. All right, and we'll draw in our implied hydrogen here. We want to know how strong these are as acids, donating these protons here. I'm going to be good and draw my triple bond with that linear geometry. All right, so here are my acids. And again, for this one, let's go ahead and cheat. We're going to go ahead and look at our pKa table here and compare. All right, so here are three acids. Carbon-carbon single bond, carbon-carbon double bond, and a carbon-carbon triple bond. Go to our pKa table here. All right. I'm going to tell you, you're going to be looking in the very last column. None of these are terribly great acids. All right, so everybody take a second, and from this last column here, find these three relevant pKa values. All right, who's got one of them? So we have our sp3 hybridized carbon. We'll have a pKa greater than 60. Notice the worst acid on our chart altogether. There's nothing worse than that. All right. What's another one? So our sp2 hybridized carbon has a pKa of 44. And what about that sp hybridized carbon? That one's up here. 25. All right, so looking at our hybridization here, an sp hybridized orbital is going to be the strongest acid. An sp3 hybridized orbital is going to be the weakest acid. All right, so why is that? It actually is just a kind of simple argument about the size of these orbitals and how closely they're held to the nucleus of that atom. Turns out that sp hybridized orbitals are a lot more tightly held to the nucleus. So when you have a negative charge in those sp orbitals, they're closer to that positively charged nucleus, making them a little bit more stable. Again, this is the last thing under consideration on our Fario list here, right? But nonetheless, if you're tied in every other way, we can compare based on these orbitals here. All right, so why sp orbitals are more closely held to that positively charged nucleus of an atom. All right, so you'll pretty much never see a sp3 or sp2 hybridized carbon losing a hydrogen. There are some special circumstances where we can use a really strong base to deprotonate these sp3 hybridized carbons, and that turns out to be very useful. We'll talk about that when we start talking about reactions in this course. Okay? But again, we spent a lot of time talking about the strength of acids here. How favorable is it to donate that hydrogen? A stronger acid gets rid of that hydrogen, donates it very easily. A weaker acid is much harder to remove that hydrogen from. Okay? And we had two ways that we could do it. One is quantitatively comparing those pKa values. The stronger the acid is the one with the smaller the pKa value. All right? Or we can qualitatively compare acid strength, meaning just looking at these structures, and we got these 5 things to consider here. The formal charge, the atom, the resonance, any induction stabilization, and the orbital, right? And again, this is a ranked list here where the most important is that formal charge and the least important is the orbital. And again, what we're really doing when we're talking about a stronger acid is we're looking at the stability of the conjugate base, right? A strong acid means that it's nice and stable after it donates that proton. So a stronger acid will have a more stable conjugate base. Cool. All right. Real quick,